Hey friends, and welcome to ASM Scientific. In this video I am gonna tell all information about our universe. The universe is everything that exists, all space, all time, all matter, and all energy. This includes the planets, stars, galaxies, and all forms of life, as well as the unseen dark matter and dark energy. It encompasses every event that has ever happened, is happening now, and will happen in the future. Essentially, the universe is the totality of existence, a vast and ever-expanding entity that holds within it all that we know and everything beyond our current understanding. In this exploration of the universe, we'll embark on a journey starting from its very inception. We'll delve into the Big Bang Theory, which describes the universe's explosive birth about 13.8 billion years ago. From there, we'll traverse the timeline of cosmic evolution, exploring how the universe expanded and cooled, leading to the formation of the first atoms, stars, and galaxies. We'll examine the large-scale structure of the universe, including the cosmic web of galaxies and clusters, and discuss the composition of the universe, highlighting the roles of ordinary matter, and dark energy. We'll also explore various fascinating phenomena such as black holes, neutron stars, and exoplanet. Moving forward, we'll discuss the expansion of the universe, guided by Hubble's law, and consider different theories about the ultimate fate of the universe, including the Big Freeze, Big Crunch, and Big Rip. Additionally, we'll touch on the intriguing possibility of a multiverse, where our universe might be just one of many. Finally, we'll look at the tools and missions that have expanded our understanding of the universe, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope. We'll place our existence in the broader cosmic context, reflecting on how astronomical discoveries have shaped our understanding of our place in the cosmos. By the end of this journey, you'll have a comprehensive overview of the universe, from its origins to its potential futures. Approximately 13.8 billion years ago, the universe as we know it began. This momentous event, known as the Big Bang, marks the origin of all space, time, matter, and energy. At the very beginning, the universe existed as a singularity, an incredibly hot and dense point where all the matter and energy were concentrated. This singularity defies our current understanding of physics, as the laws that govern our universe break down under such extreme conditions. In a fraction of a second, the universe underwent a period of rapid expansion known as inflation. This inflation caused the universe to grow exponentially, smoothing out any initial irregularities. After inflation, the universe continued to expand, but at a slower rate, allowing it to cool down gradually. This cooling process enabled energy to convert into various forms of matter. During the first few minutes after the Big Bang, a process called primordial nucleosynthesis occurred. In this phase, the extreme temperatures and pressures allowed protons and neutrons to combine and form the nuclei of the simplest elements. Hydrogen and helium, along with trace amounts of lithium, were created during this time. These elements are the building blocks of the stars and galaxies that would later form, setting the stage for the complex universe we see today. In 1965, two physicists named Arno Penzias and Robert Wilson were working with a radio antenna at Bell Labs in New Jersey. They stumbled upon a faint, persistent noise that seemed to come from all directions in the sky. After ruling out all possible sources of interference, they realized they had detected the cosmic microwave background (CMB) radiation. This accidental discovery provided a crucial piece of evidence for cosmology. The CMB is the afterglow of the Big Bang, a remnant radiation that fills the universe. It is essentially the cooled-down residual heat from the early universe, dating back to about 380,000 years after the Big Bang. At that time, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, making the universe transparent to radiation for the first time. This event, known as recombination, allowed photons to travel freely through space, and we can still detect this ancient light today as the CMB. The discovery of the CMB provided compelling evidence for the Big Bang Theory. confirming that the universe began in a hot, dense state and has been expanding and cooling ever since. It also offers a snapshot of the universe at a very early stage, allowing scientists to study its initial conditions and better understand the processes that led to the formation of galaxies, stars, and ultimately, the universe we observe today. Galaxies are massive systems composed of billions of stars, along with gas, dust, and dark matter, all held together by gravity. They come in various shapes and sizes, including spiral galaxies like our Milky Way, which features a central bulge surrounded by rotating arms of stars and gas. Another example is the Andromeda Galaxy, our closest spiral neighbor. Elliptical and irregular galaxies also populate the cosmos, each with unique structures and characteristics. Galaxies are not randomly scattered but are grouped together into clusters. A galaxy cluster can contain hundreds or even thousands of galaxies bound by gravity. These clusters, in turn, are parts of even larger formations known as superclusters. For instance, the local group, which includes the Milky Way and Andromeda, is part of the Virgo supercluster. Superclusters represent some of the largest known structures in the universe. On the grandest scales, the universe's structure resembles a cosmic web. This web consists of vast filaments of galaxies and dark matter, with immense voids of nearly empty space in between. These filaments intersect at nodes, where galaxy clusters and superclusters are densely packed. The cosmic web's intricate, interconnected pattern is a result of gravity acting on matter over billions of years, shaping the large-scale architecture of the universe. This structure helps scientists understand how matter is distributed and how the universe evolved from its early, nearly uniform state to the complex tapestry we see today. Ordinary matter, also known as baryonic matter, constitutes about 5% of the universe. This includes everything we can see and touch: stars, planets, galaxies, and all other visible structures. Atoms, which are composed of protons, neutrons, and electrons, make up this ordinary matter. It's the stuff that forms the Earth and all life on it, the light-emitting stars, and the interstellar gas and dust. Dark matter makes up approximately 27% of the universe. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. It is essential for explaining the observed rotation speeds of galaxies and the gravitational lensing of light from distant objects. Without dark matter, the gravitational pull within galaxies and clusters would be insufficient to hold them together. Despite its significant presence, the exact nature of dark matter remains one of the biggest mysteries in astrophysics. The most dominant component of the universe, dark energy, accounts for about 68% of the total. Dark energy is a mysterious force driving the accelerated expansion of the universe. Its discovery was a major breakthrough in the late 20th century when observations of distant supernova revealed that the universe's expansion rate is increasing. While dark energy's exact properties are still not well understood, it is thought to permeate all of space, acting as a sort of anti-gravity that pushes galaxies apart at an ever-increasing rate. This accelerated expansion has profound implications for the ultimate fate of the universe. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. They form when massive stars collapse under their own gravity after exhausting their nuclear fuel in a supernova explosion. The boundary surrounding a black hole where escape velocity equals the speed of light is called the event horizon. Beyond this point, the gravitational pull becomes infinite. Black holes come in different sizes, from stellar mass black holes, which are several times more massive than our Sun, to supermassive black holes found at the centers of galaxies, weighing millions or even billions of solar masses. Black holes are crucial to our understanding of general relativity and play a vital role in shaping the evolution of galaxies. Neutron stars are incredibly dense remnants left behind after massive stars undergo supernova explosions. These stars are composed almost entirely of neutrons, packed tightly together. A neutron star typically has a mass comparable to that of the Sun but is squeezed into a sphere only about 20 kilometers in diameter. The intense gravity on a neutron star's surface creates extreme conditions, including powerful magnetic fields and rapid spin rates. Neutron stars emit beams of radiation that can be observed as pulsars if the beams sweep past Earth periodically. These exotic objects provide insights into the behavior of matter under extreme densities and magnetic fields. Exoplanets are planets that orbit stars outside our solar system. The discovery of exoplanets has revolutionized our understanding of planetary systems and their diversity. The first confirmed detection of an exoplanet orbiting a main sequence star was made in 1992, and since then, thousands of exoplanets have been discovered using various techniques, including the transit method, radial velocity method, and direct imaging. Exoplanets vary greatly in size, composition, and orbital characteristics, ranging from gas giants similar to Jupiter to rocky planets similar to Earth. Studying exoplanets provides insights into planetary formation processes, habitability conditions, and the prevalence of Earth-like worlds in the universe. Hubble's law, discovered by astronomer Edwin Hubble in the 1920s, describes the relationship between the distance of galaxies from Earth and their recessional velocity. Simply put, galaxies appear to be moving away from us, and the farther away they are, the faster they appear to be moving. Hubble's groundbreaking discovery provided strong evidence for the expanding universe theory, indicating that the universe is not static but rather undergoing a continual process of expansion. This expansion implies that at some point in the past, all matter and energy in the universe were concentrated in a single point during the Big Bang. One of the key pieces of evidence supporting Hubble's law is the phenomenon of redshift. As galaxies move away from us due to the expansion of the universe, the light emitted from them is stretched to longer wavelengths, shifting towards the red end of the spectrum. This effect is known as cosmological redshift. Redshift occurs because the space between galaxies stretches as the universe expands, causing the wavelength of light to stretch along with it. The amount of redshift observed in the light from distant galaxies is directly proportional to their distance from us, aligning perfectly with Hubble's law. By measuring the redshift of galaxies, astronomers can determine their velocity relative to us and calculate their distance from Earth. Together, Hubble's law and redshift provide compelling evidence for the dynamic nature of the universe, showing that space itself is expanding and carrying galaxies away from each other. This understanding has reshaped our cosmological models, revealing a universe that began in a hot, dense state and has been expanding ever since, evolving into the vast and complex structure we observe today. The Big Freeze, also known as heat death or the cold death, posits a future for the universe based on current understanding of its expansion and thermodynamics. In this scenario, the universe continues expanding indefinitely, causing its energy to progressively thin out. Stars eventually burn out, leaving a dark and frigid cosmos where all celestial bodies cool to near absolute zero. Galaxies drift apart, interactions between them become rare, and only remnants of dead stars, black holes, and sparse particles remain scattered across vast empty spaces. The Big Crunch, on the other hand, is a theoretical reversal of the universe's expansion driven by the gravitational pull of all matter and energy within it. If the universe's density is sufficiently high and dark energy does not prevent it, gravity could overpower expansion, leading to a collapse where galaxies, stars, and all matter converge towards a central point. This reversal culminates in a fiery end resembling a reverse Big Bang. In contrast, the Big Rip presents a more extreme and speculative scenario where dark energy, driving accelerated expansion, continues to intensify. Eventually, its repulsive force becomes dominant enough to overcome gravitational forces that bind galaxies, stars, planets, and even particles. This cataclysmic expansion would tear apart all cosmic structures, including spacetime itself, resulting in the dissolution of everything in the universe. These scenarios illustrate potential fates based on varying assumptions about the universe's composition, expansion dynamics, and the interplay between dark energy and gravity. Understanding these outcomes is pivotal for cosmologists as they explore the ultimate destiny of the universe and everything within it, including ourselves. The multiverse theory proposes that our universe may be just one of many universes that exist. Each of these universes, often referred to as parallel or other universes, could have different physical laws, constants, and even dimensions than our own. The idea challenges the notion that our universe is unique and isolated, suggesting instead that it is part of a vast and diverse cosmic ensemble. In the context of eternal inflation theory, our universe could be one of many bubble universes within a larger multiverse. These bubbles form independently and can have different properties based on quantum fluctuations during the rapid inflationary phase of our universe's early history. According to the many worlds interpretation of quantum mechanics, every possible outcome of every quantum event spawns a new universe. This theory suggests that every decision, every random event, and every quantum interaction could result in a branching universe, creating an infinite number of parallel realities. Based on string theory, the brane multiverse posits that our universe is a three-dimensional brane floating within a higher dimensional space. Other branes may exist parallel to ours, each potentially with its own set of physical laws and particles. Collisions or interactions between these branes could create new universes or influence existing ones. The mathematical multiverse hypothesis suggests that every mathematical structure or possibility defines its own universe. This concept arises from the idea that mathematics is not just a tool for describing the universe but could be the fundamental fabric of reality itself. Thus, every conceivable mathematical structure would exist as a physical reality in its own universe. The concept of a multiverse has profound implications for our understanding of existence, the laws of physics, and our place in the cosmos. It challenges traditional notions of cosmology and raises questions about how we define and explore the boundaries of our universe. While the idea of a multiverse remains speculative and difficult to test empirically, it continues to intrigue and inspire physicists, cosmologists, and philosophers alike, offering new perspectives on the nature of reality and the possibilities beyond our observable universe. Hubble Space Telescope launched in 1990, the Hubble Space Telescope has revolutionized astronomy with its ability to capture high-resolution images across a wide range of wavelengths, from ultraviolet to near-infrared. Hubble has provided crucial data on the expansion rate of the universe, the formation of galaxies, and the presence of supermassive black holes at the centers of galaxies. Scheduled for launch, JUICE promises to be the successor to Hubble. Operating primarily in the infrared spectrum, JUICE will study the formation of stars and planetary systems, the early universe, and the atmospheres of exoplanet. Its advanced capabilities will enable astronomers to peer deeper into space and further back in time than ever before. Wilkinson Microwave Anisotropy Probe WMAP, launched in 2001, WMAP provided detailed measurements of the cosmic microwave background (CMB) radiation. It mapped tiny temperature fluctuations in the CMB, offering insights into the early universe's density variations, age, and composition. WMAP's data significantly supported the Big Bang theory and helped refine cosmological parameters. Operated by the European Space Agency from 2009 to 2013, the Planck satellite continued WMAP's mission of studying the CMB with even higher precision. Planck's observations refined our understanding of the universe's age, composition, and fundamental parameters, including dark matter and dark energy. Various space missions, such as the Cosmic Background Explorer (COBE), the Spitzer Space Telescope, and the upcoming Euclid mission by the European Space Agency, focus on studying cosmic background radiation, dark matter, and the large-scale structure of the universe. These missions employ advanced technologies and observational techniques to unravel the mysteries of the cosmos. Cosmological tools and space missions have played pivotal roles in advancing our understanding of the universe. They have provided empirical evidence for cosmological theories, confirmed the existence of dark matter and dark energy, and shed light on the early universe's conditions and evolution. By utilizing telescopes and conducting precise measurements from space, astronomers continue to push the boundaries of knowledge, unveiling new insights into the universe's origins, structure, and ultimate fate. These tools not only deepen our scientific understanding but also inspire new generations to explore the mysteries of the cosmos. Earth, our home, occupies a relatively humble position in the grand scheme of the universe. Located in the Milky Way galaxy, a barred spiral galaxy roughly 100,000 light-years in diameter, Earth orbits around an average star known as the Sun. Within the Milky Way, which contains hundreds of billions of stars, our solar system resides in the Orion Arm, a minor spiral arm stretching outward from the galactic center. In the context of the observable universe, which spans billions of light-years, our galaxy is just one among many. The Milky Way itself is part of a larger galactic group called the Local Group, which includes over 54 galaxies, such as the Andromeda Galaxy and the Triangulum Galaxy. Throughout history, astronomical discoveries have profoundly shaped our understanding of the universe and our place within it. From the Copernican revolution, which displaced Earth from the center of the universe, to the discovery of galaxies beyond our own, each breakthrough has expanded our cosmic perspective. The realization that the Milky Way is just one of countless galaxies shifted our perception from a solitary island in space to a member of a vast galactic community. Observations by Edwin Hubble in the 1920s demonstrated that galaxies are receding from each other, providing evidence for the expanding universe and the Big Bang Theory. The discovery of exoplanet-orbiting stars beyond our solar system has ignited excitement about the possibility of extraterrestrial life. Identifying over 4,000 exoplanets has shown that planetary systems are common in the universe, fostering speculation about habitable worlds and the diversity of potential life forms. The detection of the cosmic microwave background (CMB) radiation provided compelling evidence for the Big Bang Theory and offered a glimpse into the universe's infancy, just 380,000 years after its birth. These discoveries not only enhance our scientific knowledge but also evoke a sense of wonder and curiosity about the cosmos. They challenge us to reconsider our place in the universe and contemplate our role as inhabitants of a planet orbiting an ordinary star in an extraordinary galaxy. The ongoing exploration of the universe continues to inspire new questions and discoveries, inviting humanity to explore and understand the mysteries of existence on a cosmic scale. If you like this type of videos, then like this video and subscribe my channel. See you in the next video.